Today we're going to look at acids and bases. When we talk about acids and bases, we should have an idea of what the properties are. For acids, they have sour taste, and they have ability to dissolve many metals. To dissolve many metals. And they have the ability to neutralize bases. Of course, they change blue litmus paper to red. Blue litmus paper to red. These are the properties of acid. We have different types of acid like hydrochloric acid, sulfuric acid, acetic acid, carbonic acid, and so on. So, and when we look at bases, we also have properties of bases, right? They taste bitter. They have soapy feeling, or we say they feel slippery. And they have the ability to turn blue litmus paper. I'm sorry. They turn red litmus paper blue. Red litmus blue. And of course, they also have the ability to neutralize acid. Neutralize acid. So these are properties of bases. We have common bases. Examples are sodium hydroxide, potassium hydroxide, sodium carbonate, and so on and so forth. So we want to look at definition of acids and bases. Definition. Acids and bases. So let's look at Arrhenius' definition. So according to Arrhenius, an acid produces hydrogen ion in solution. So according to Arrhenius, acid produces hydrogen ion in solution. So hydrogen ions are always associated with water to form hydronium ion. So for an acid, anything that produces a hydrogen ion in solution is an acid. And according to Arrhenius, a base is anything that produces a hydroxide ion in solution. Anything that produces hydroxide ion in solution. That is Arrhenius' definition of acid and base. So the next thing we want to look at is Bronsted-Lewis definition. Bronsted-Lewis definition. So Bronsted-Lewis definition of an acid is a proton donor. And a proton is hydrogen ion. And according to him, a base is a proton acceptor. Anything that accepts a proton is a base. So, according to Arrhenius, if you have hydrogen, if you have HCl, it's going to dissociate into this aqueous, and this is aqueous, and it's going to dissociate into that. So that is going to be our Arrhenius acid. So we have for a base is going to be sodium hydroxide. Aqueous is going to dissociate into sodium aqueous plus hydroxide aqueous. So there is something that is common about definition of Arrhenius acid and Brustolewicz. Brustolewicz definition of an acid is broader than the Arrhenius because we have some bases that do not produce OH hydroxide ion whenever they dissolve in whenever they dissociate. For example, ammonia is a base. However, ammonia is not going to dissociate to produce hydroxide ion. So, Brustolewicz definition of an acid, we say, is a proton donor and proton acceptor becomes acceptable into this. So, we have what we call Brustolewicz acid, which are hydrogen donors, and we have Brustolewicz bases, which are hydrogen acceptor. According to Brustolewicz, we can also say that when HCl dissolves in water, it's going to be an acid, Brustolewicz. HCl is going to dissolve in water. HCl aqueous is going to dissolve in water, right? To have what we call this and hydronium ion. So when HCl dissociates in water, the HCl is an acid because the HCl transfers hydrogen ion to water molecule. And water in this case is acting as a base because accepting hydrogen ion. We can see that the hydrogen leaves this HCl here, and we have chloride ion standing alone. So that is a proton that is being donated from HCl to water molecule to form the hydrogen ion. So in this case, HCl is an acid because it is a proton donor. And the water is going to act as a base because it is accepting a proton to form this hydrogen ion. So we have what we call amphoteric substance. Amphoteric substances can act as either an acid or a base because they have both transferable hydrogen and an atom that has lone pair of electrons. So amphoteric substances can act as well either an acid or a base. They can act as either as an acid or a base. Let's take a look at an example we have done before. We have HCl plus H2O to give this and H2O. And we also have ammonia plus H2O liquid. And we have ammonium ion being formed. And we have OH, aqueous. Okay, this is a liquid and this is aqueous. And we have aqueous and we have liquid. So in this first equation here, this is an acid, this is a base. Water is a base here because it's upsetting this proton from hydrogen. In this case, we can see that water is acting as an acid because we have hydrogen leaving a water molecule to water is donating hydrogen ion to ammonia here to form our ammonium ion. So it's acting as an acid, while ammonia is acting as a base. So we can say that water in this case is an amphoteric substance. So that is an amphoteric substance. Yes. We also have what we call conjugate base. Conjugate acid base pair. Acid base pair. In Bronsted-Lowry acid base reaction, the original base becomes an acid in the reverse direction. And the original acid becomes a base in the reverse process. So, say original base becomes an acid in the reverse direction. And the original acid becomes a base. Original acid becomes a base in the reverse direction. So each reactant and the product is called conjugate pair. So we now say each reactant and the product becomes conjugate pair. All right. So let's take an example from the the reaction that we already did for atmospheric substance, which we have ammonia and water. In this, which we have ammonium ion plus our hydroxide ion. Okay, we already established that this water here is an acid and ammonia is our base. So in the forward direction, we have this as a base and this as an acid. When we go to the product side, so this becomes the conjugate acid. And if this is our conjugate acid, and this becomes our conjugate base automatically. So a base accepts a proton and it becomes a conjugate acid. And an acid donates a proton and it becomes a conjugate base. So this is what I mean. We have our base here, right? And our base accepts a proton, right? So become this. So when it becomes this, it is now the conjugate acid. And our acid here, which is water, it donates the proton and it becomes, when it donates the proton, that is a proton or hydrogen leaves water, it becomes this, OH. And when that happens, we say our OH is the conjugate base. So we have to remember that a base accepts proton and becomes conjugate acid. An acid donates a proton and becomes conjugate base. So this is how we get to be able to figure out conjugate base and conjugate acid. We can know the strength of acid and we can know the strength of bases. So acid strength. A strong acid is a strong electrolyte, right? Any strong acid is going to be automatically be a strong electrolyte. Because practically, if you have a strong acid, practically all the acid in the molecules, they are going to ionize. So we say they are strong electrolytes. The same way, a strong base is also we of course automatically be strong electrolyte as expected. Because practically all the base molecules from hydroxide ion or either through dissociation or reaction with water is going to be all the molecules we ionize. So we should expect that. And a weak acid is going to be weak acid. Weak acid will be weak electrolyte. And because they are not going to be fully ionized when the molecules are not going to be ionized. So of course, a weak base, we also be a weak electrolyte. Weak base will also be weak electrolyte because of they're going to partially ionize. All right, so we can look, we have so many examples of weak acids and weak base. So let's look at the acid ionization constant, Ka. Acid ionization constant, Ka. An acid strength is measured by the size of the equilibrium constant when it reacts with water. Sure, we are all familiar with equilibrium constant expression. So the equilibrium constant for this reaction is called the acid ionization constant, Ka. Let's take a look at the example of what I'm saying. Let's say this is our acid, right? And we have it in this way. So this is aqueous. This is H2O liquid. And it's forming so this is aqueous, and this is going to be HIA negative, right? So we can write the equilibrium constant expression for this reaction. So, and we know that this is liquid. We do not include this in the equilibrium constant expression. So our Ka, which is the equilibrium constant for this reaction, and which is going to be, we call it acid ionization constant, Ka, K of acid. So it's going to be Ka equals to, remember our equilibrium constant expression, it's always the concentration of product over the reactant. So in the product, we're going to have hydrogen ion concentration multiplied by this over, of course, we're not going to include water in our expression. It's going to be like our HA in AQ. So that becomes our Ka. Or better still, this hydrogen ion can also be represented as hydrogen ion, and we can have it in this way, HA. So that becomes our Ka. And we know the larger the Ka, the stronger the acid is going to be, right? From our knowledge of equilibrium constant. If Ka is large, so it means our acid is going to be strong. Larger Ka is equivalent to stronger acid. So with this statement, if you are given various Ka values for different acids, you can be able to distinguish which acid is going to be stronger and which of the acid is going to be a weak acid. Let's take, for example, I have HF. Ka for HF is 6.8 times 10 to negative 4. And I have another acid here. The Ka is given as 2.9 times 10 to negative 8. We have different values for Ka. So this Ka, we can use the Ka value to determine which of these two acids is going to be stronger. So because of this value, we know that this is 10 to the power -4, this is -8. Definitely this is smaller, right? So the stronger acid is going to be our our HF, because this is smaller and this is a larger value. So we use that to know if our acid is going to be strong or a weak acid. So we have the ion products of water. The products of hydrogen ion concentration or hydrogen ion concentration and hydroxide ion concentration is always the same number. The number is called the ion product of water, and it has the symbol of W. It's the product of and OH. It's always the same number, and we call it KW. And our KW is called, or it is a symbol for the ion product of water. And it's also known to be the dissociation constant for water. Dissociation constant for water. So at 25 degrees C, our KW is going to be the concentration of hydrogen ion and concentration of hydroxide ion, and it's going to give us 1.0 times 10 to -14. Okay. So this gives us this value. So we have the dissociation constant for water to be that. So as hydrogen ion increases, automatically we expect that hydroxide ion concentration must decrease so that this value can remain constant. We call it dissociation constant. So if our hydrogen ion increases, our OH must decrease so that this value of this KW can remain constant. So we use that to make calculations. We can use that to find the hydrogen ion concentration of our solution or whatever we have. So neutral solutions have equal quantity of hydrogen ion concentration and hydroxide ion concentration. So it means that if you have a neutral solution have hydrogen ion concentration to be equal to the hydroxide ion concentration, and that is going to be 1.0 times 10 to -7 molar. Acidic solution have a larger hydrogen ion concentration than hydroxide ion concentration. So if our solution is acidic, right, acidic solution, we're going to have our hydrogen ion concentration to be greater than 1.0 times 10 to negative 7 molar. And our hydroxide ion concentration is going to be less than 1.0 times 10 to negative 7 molar. So we need to remember all this because we can use this to check if our solution is acidic or our solution is basic. For basic solution is just the reverse, right? For basic solution, our hydrogen ion concentration is going to be less than 1.0 times 10 to negative 7 molar. And our hydroxide ion concentration will be greater than 1.0 times 10 to negative 7 molar. So let's check using this example. If you have hydrogen ion concentration to be equal to 1.0 times 10 to negative 3 molar, and we have hydrogen ion concentration to be 1.0 times 10 to negative 7 molar. We also have this to be 1.0 times 10 to negative 8 molar. At room temperature, which of these is going to be acidic? So we just need to look at the values of this. So at room temperature, we're going to have, this is A, B, C. So at room temperature, this one is going to be the most acidic solution that we have. At room temperature, we're going to have this to be the most acidic solution. How do we measure acidity? We measure acidity using pH, which means power of hydrogen. The acidity or basicity of a solution is often expressed as pH, and pH is the negative log of hydrogen ion concentration. So for water, the pH of water that we drink is negative log of hydrogen ion concentration, which is 10 to power negative 7. And if you solve that in our calculator, it's going to give us 7. So we need to know the hydrogen ion concentration to find pH. If the pH is less than 7, it is acidic. And if the pH is greater than 7, it is neutral. That is pH less than 7 is acidic. pH greater than 7 pH greater than 7 is basic. We use this relationship to find the pH of our solution. So for you to know the pH, we need to know what our hydrogen ion concentration is. Very important. And we can use, if we know the hydrogen ion concentration and we want to find the pH, we can solve this equation by saying, we can say our hydrogen ion concentration is equal to 10 to negative pH. 10 to negative pH. So we can use this to solve problems, because we can be given the pH, we can be asked to find the hydrogen ion concentration. For instance, if the pH of a solution is given to be, is said to be, let's say 8.9, find hydrogen ion concentration. So just like if you find pH from hydrogen ion, you can find that. So what you just need to do is to plug in, use this equation that we have here. So it's going to be your hydrogen ion concentration is going to be 10 to negative 8.9. When you plug that into your calculator, whatever it gives you, you see your response. All right. So we also have POH, which is POH. So another way of expressing the acidity or basicity of a solution is using POH. Right. And POH is given as negative log of hydroxide ion concentration. And we can also find even the POH, we can find the hydroxide ion concentration as well, which is going to be equal to 10 into negative POH. If you're given the hydroxide ion concentration and not the hydrogen ion concentration, if you plug the value of the hydroxide ion concentration into your expression, what you are finding is POH. So, but however, you can still find the pH using the POH, right? So we say that POH plus pH is going to be 14. It's going to be equal to 14. This is how you solve that. All right. For POH of water, POH of water is still negative log of 10 to negative 7, and it's still going to give you 7. And like I said, if you want to find the POH, what you need is your hydroxide ion concentration to find the POH, not hydrogen ion. So when the POH is less than 7, the solution is basic. So when the POH is greater than 7, the solution is going to be acidic. Of course, when the POH is equal to 7, the solution is neutral. And of course, we can find the POH, the pH, when we know the POH, we can find the pH. Just using the previous expression, POH is plus pH. POH plus pH is 14. So if you know the POH, your pH is going to be 14 minus POH. So this expression is very important. So we can use the dissociation constant of water to find the pH or pOH or whatever we want to find. So I would like us to solve more examples on finding pH, pOH, and using the hydrogen ion and hydroxide ion concentration